Okay, let's get on to problem 47, and it's also about a set S of vectors, which we're going to establish now. So we enter the elements as a row vector and visualize it as a column vector. That's the first vector, and now we do the same with the second vector, and look at that as a column matrix. And then we do the third vector and visualize that using this. The first thing they want us to do is to show that the vectors v1, v2, v3 are linearly dependent, and if so, that is so, show that at least one of the vectors can be written as a linear combination of the others and find that linear combination. And then the third part is given some vector whose elements can be written like that and visualize as a column matrix, show that express that as a linear combination, or find all possible ways of expressing that vector as a linear combination of the vectors in S, and then to find a linearly independent subset of S with the same span of S, and show that the vector in C, that is this guy here, can be written as a linear combination of the vectors in this subset, and then finally give a geometric interpretation of the span of S. Okay, so let's start at the beginning with the first part. So as we did in the previous example, we make a matrix whose columns are the three vectors here, which we can do using this and visualize it using this. And so these vectors are linearly independent if the matrix this matrix here is singular. So let's do the row reduction, because if this matrix is singular, then its determinant is 0. So let's do the first step of the row reduction. So we add 3 times the first row to the second and twice the first row to the third. So we can do that using this and check that everything's as it should be using this, and we can see that that this element of the subdiagonal elements in the first column are now 0. And then we carry out the second phase of the row reduction, so we add 7 times the second row to 11 times the third row, like so, and then we can visualize that like so. And we can see that the determinant of this matrix, which is the product of the diagonal elements, is 0. The third row is also the 0 vector, so that these two vectors are linearly dependent. And now we want to express the third vector, for example, as a linear combination of the first two. So we can do that if we can find unique values of the parameters a and b, which we can establish using this, such that the third vector is a linear combination. So we take a times the first vector plus b times the second vector and subtract off the third vector, and if that's possible, then we should be able to find the coefficients a and b, unique values, in such a way that that these three equations here vanish. So let's find the coefficient matrix, and we can visualize that as a matrix using matrix form, and then there it is. Now we can find the right-hand side vector of the equations by multiplying the coefficient matrix by the parameters and subtracting off the equations. So we execute that, and then we can view that as a column matrix, like so. So we now do row reduction of the augmented matrix. So we add, for each row of the coefficient matrix, we add the corresponding element of the right-hand side vector, which we can do using this, and that produces us the augmented matrix, which we can check using that. So that's all good. And now we carry out the row reduction, so it's the same as before. So we add 3 times the first row to the second, and twice the first row to the third. And we can do that using that, and then visualize that, and then we add 7 times the second row to the third row, to 11 times the third row, and we'll subtract it from it, and we get that, and we can view that. So this is the same as we got before, except, or similar to what we got before, except now that the bottom row is 0, and if we think of that as a linear equation, it says that 0 equals 0, which is what we would hope. And now we want to generate the equation for the parameters from the second row. So we take the second row, and we multiply it by the vectors, the parameters, and we get that. So that would be 11b is equal to 11, and therefore the solution can be easily found to be, by setting that equal to 0 and solve, gives us b equals 1, and then we now work out or write down the equation from the first row, and we use this value of b in it, and we can see that this is an equation for a, and we can solve that quite easily to get a equals 1. And now we check that we've got the solution, so we regenerate the original equations like so, and then we insert the solutions we've got, and that should be the same as the third vector, which it is. So we've found that v1 is equal to v3, is equal to v1 plus v2. So that's what we were after. And now we want to express this vector here as a linear combination of the vectors in S. So we take a linear combination of those vectors, a times the first one plus b times the second one and c times the third one, and then we subtract off this vector, which we called v, and that should give us an equation, a set of equations for the parameters a, b, and c, which we can establish using that. And now we dig out the coefficient matrix, and we can visualize that in matrix form. Using, and now we just write There we go, and there it is. We've seen this before. And to get the right-hand side vector, then we multiply the coefficient matrix by the parameters and subtract off the original equations, and that should give us the right-hand side vector, and we can visualize that using that, and that's the vector that we're asked to find we'll find a linear combination. So we use our tool for finding the augmented matrix using this, and visualize it using that. So we want to do row reduction on that matrix, on the augmented matrix, and that will give us a solution of the equation. So it's the same story as before, 3 times the first row to the second, and twice the first row to the third, and then so that's the first stage of the row reduction, and we can visualize that. And now we have to subtract 7 times the second row from the third row, keeping the first 2 rows unaltered, and that gives us that. And now we can visualize that in matrix form, and we can see that remembering that is the augmented matrix for a set of linear equations, we can see that the last equation is 0 equals 0, which is of course trivially satisfied. So we now go to the second row and generate the equations by taking the scalar product of the second row of the augmented matrix with the vector consisting of the 3 parameters plus the element -1. And that gives us this equation, which is an equation connecting B and C. So we can regard C as a parameter and solve that for B, to give B as 3 minus C. And then we get a second equation by taking the scalar product of the first row of the row reduced matrix with the vector of parameters, and put in the solution for B, and this gives the left-hand side of an equation for A, which we can set equal to 0 and solve for A using this. And then we can check that we've got the right answer, because we can regenerate the equations by multiplying the coefficient matrix by the parameters and inserting our solutions for A and B, and that is indeed the vector we were asked to find the linear combination of. So in other words, for any value of C, this linear combination here and here is equal to the given vector. So that's all possibilities.